Hey everyone, this is Andrew. Welcome back to the channel. In this organic chemistry video, I will be discussing spectroscopy and the electromagnetic spectrum. As an organic chemistry student, the four kinds of analytical techniques that you're going to come across include infrared, ultraviolet, and nuclear magnetic resonance spectroscopies, as well as mass spectrometry. Infrared, ultraviolet, and NMR differ from mass spec in that they are non-destructive and involve the interaction of molecules with electromagnetic energy rather than an ionizing agent, such as electrospray ionization. Like all kinds of waves, electromagnetic radiation is characterized by a wavelength, a frequency, and an amplitude. The wavelength, or Greek lambda, is the distance from one wave maximum to the next. The frequency, Greek nu, is the number of waves that pass by a fixed point per unit time, usually in reciprocal seconds, or hertz. The amplitude is the height of a wave measured from midpoint to peak. So when an organic compound is exposed to a beam of electromagnetic radiation, it absorbs that energy of some wavelengths, but it passes or transmits energy of other wavelengths. If we irradiate the sample of a specific organic compound with different sorts of wavelengths and then determine which are absorbed and which are transmitted, we gain what is called an absorption spectrum of the compound. The energy a molecule gains when it absorbs this radiation must be distributed throughout the molecule. With infrared radiation, the absorbed energy causes the bonds to stretch and bend extremely vigorously. So why does an organic molecule absorb some wavelengths of IR but not others? All molecules have a certain amount of energy and are in constant motion. Their bonds stretch and contract. Some atoms move in back and forth direction. That's where we get the symmetric stretching, anti-symmetric stretching. The amount of energy that a molecule contains is not continuously variable, but is instead quantized. This means that a molecule can stretch or bend only at specific frequencies, corresponding to specific energy levels. So when a molecule is irradiated with electromagnetic radiation, energy is absorbed if the frequency of the radiation matches the frequency of the vibration. So since each frequency absorbed by a molecule corresponds with a specific molecular motion, we can find what kinds of molecular motions are occurring, and by interpreting and measuring these motions, we can find out what kinds of functional groups are present in the molecule, in the compound. The complexity of these absorption spectrums can be a bit overwhelming, but I like to think of them as unique fingerprints for each molecule. If two samples have identical IR spectra, then they are certainly the same molecule. They are certainly identical compounds. Let's take a look at this table. What we have here are characteristic infrared absorptions of some functional groups, some key functional groups. So what do these numbers mean? What does the intensity mean? So let's take a look. An alkane with a carbon atom that is sp3 hybridized will absorb the radiation between 2850 and 2960. This intensity of this peak will be medium, meaning it won't go all the way down to the bottom, but it also won't be up at the top. It's gonna be somewhere right in the middle. It won't be very broad. It won't be very slim. It will just be a perfect looking curve in a way, if that makes sense. It's not gonna be too broad. You'll see when we get to the alcohols and carboxylic acids. Those have very broad, strong peaks. Now, a carbon atom that has a pi bond and a sigma bond, a double bond, coming from some R group bonded via a sigma bond to a hydrogen atom will absorb between 3020 and 3100. And that's going to have a medium peak, a medium intensity. Now, a pi bond and a sigma bond, a double bond between two carbon atoms will absorb between 1640 and 1680. You can just memorize, if you're looking at a absorption spectrum and you're on an exam or something, it's going to be between 1600 and 1700 most likely, and it'll have a medium intensity. Now, a carbon atom that is sigma bonded to a hydrogen with two pi bonds coming from an R group and a sigma bond will absorb around 3300. That's going to be a very strong peak. And a triple bond between two carbon atoms absorb around 2100, between 2100 and 2200, 2260 to be exact. And that's going to be a medium peak. Take a minute, pause the video. You can write these down. Most every single organic chemistry textbook will have these numbers though. So I find these extremely crucial as well. These numbers right here for alkyl halides, those show up in the fingerprint region. The fingerprint region is everywhere below 1500 reciprocal centimeters on the absorption spectrum. And the peaks for these alkyl halides are extremely strong. They'll look like this. They'll have a very steep peak like that. Alcohols are extremely fun to pick out on an IR spectrum because they're extremely easy. They're extremely strong, broad peaks, and they show up between 3400 and 3650. Now, on the other hand, a carbon atom that is sigma bonded to a oxygen atom will show up extremely lower than that, between 1050 and 1150. Now I've gone ahead and boxed in some of the most important ones: alkanes, alkenes, alkynes, alkyl halides, alcohols, carboxylic acids, carbonyl compounds, and amines. These are some of the most important absorption spectra to remember moving forward. The ability to differ between carbonyl compounds is crucial, especially aldehydes and ketones. Now a number like 1735 isn't exactly extremely important to remember on an exam. However, if you're working in a laboratory, working with synthesis, you're going to want to know exactly the product that you formed. So knowing these, that's where that comes in handy. Here's a quick example just to test out what we learned. This is a molecule of hexane. As we can see, it's a simple alkane. The sp3 hybridized carbon atoms show up right here, right below 3000, specifically between 2800 and 2960. Here's another quick example. Moving from an alkane to an alkene, 1-hexene. We see the crucial bonds here. We have sp3 hybridized carbon atoms right there. Right here, this is extremely important. You have the sp2 hybridized carbon atom bond to a hydrogen via a sigma bond. That's this peak, right around 3100 or so. It's not exactly to scale, but. And then we have here sp2 hybridized carbon atoms bonded together via a pi and sigma bond. That's what this important peak is right here. Moving from an alkene to an alkyne, we take this up another notch. Here, this is the triple bond peak. That's what's crucial right there. Then we also have a triple bond peak right here between two carbon atoms, which shows up right around 2100. So here we see that we got sp3 hybridized atoms between 4000 and 2500. We have sp hybridized atoms between 25 and 2000. Then we have sp2 hybridized atoms between 2000 and 1500. 1500 is where the fingerprint region comes into play. Everything below that on the spectrum is in the fingerprint region. Like I said, if you're looking for some more information on fingerprint, go in your textbook and read that, or find someone like a professor who has had experience in the fingerprint region to teach you more so on that. So first practice problem. Let's take a look at the options. First, we have a carboxylic acid. Next, we have an alcohol. Third, we have a nitro group. And then fourth, we have an aldehyde. This one is fairly easy. Like I told you, the alcohol peaks are extremely easy to pick out. There's only one option for an alcohol, so we know that it's going to be option 2. The cyclohexanol is going to be the answer. If you want to go further, we see here that we have sp3 hybridized carbon atoms bonded to a hydrogen atom. That's that peak right below 3000. And then the fingerprint region, like I told you, those peaks are crucial. However, for this case, it's fairly easy to pick this answer since there is only one alcohol peak. So here's another problem. Right from the get-go, we can immediately cross out the alcohol. There is no alcohol peak. If there was an alcohol peak, it would be looking like that, along the lines of that. There is no prominent peak around 1740 or so we can cross out the ketone. But this peak right here is interesting. Amines absorb between 3,300 and 3,500. So this peak is crucial as we move forward because there's only one option with the amine group attached. So what we have here is a cyclohexylamine. We know it wouldn't be the nitro. There is no prominent peak around 1540 or so. If it was the nitro, this peak around here would go very deep. It'd be around like that, and we don't have that. So we know that's not the nitro group. So the answer is the cyclohexylamine. So let's take a look at this one. This, straight off the bat, we know here we have an alcohol group. So you're going to want to write that down immediately. You know that the alcohol group is strong and broad and it absorbs between 3,000 and 3,500, just like this. It's going to look something huge like that all the time. So look, we see here we only have one alcohol option. However, let's move forward and continue interpreting this spectra. Here we have the sp3 hybridized peak for a carbon atom that is sigma bonded to a hydrogen. That's what this thing is right here, right below 3000. The carboxylic acid, however, is extremely interesting. The carboxylic acid would absorb something like this around 3000. It's not going to be nearly as strong or broad as the alcohol. However, it will show up, so don't get tricked by that. If you ever see this peak that's absorbing like this strong and broad, it is most definitely an alcohol. So pick it. And now if it comes down between two options where the alcohol is in the compound, that's where you start moving over to the right towards the fingerprint region. The answer is the alcohol. Okay, so last example, let's take a look at the spectra. Let's take a look at our options first. What we see here is we have a cyclohexene ring. You know, the sp2 hybridized carbon atoms absorb between 1600, 1700. That's for the two carbon atoms bond together. However, we also have hydrogens coming off, remember. So the carbon atoms bond to the hydrogen pick up around 3,000, between 3,000 and 3,200. So we see here we have an alkyne. Alkynes are sp hybridized. The carbon atoms are sp hybridized, and they pick up. Their absorption is very high, around 3,300. for this one, which has a hydrogen coming off. This one would pick up around between 21 and 23. And now over here we have a ketone. This picks up somewhere around 1700 or so. So when we take a look at this, let's see what we got. We know this peak right around this area is for sp3 hybridized carbon atoms, which all the molecules have, so it's not that big of a help. This peak, however, is extremely interesting. This is for sp2 hybridized carbon atoms, sigma bonded to hydrogen atoms. So by looking at this, we know we can cross off this one. There is no peak up in that area for the alkyne, and there is no major peak in this area for the sp hybridized carbon. Now the ketone, we do see that we have peak somewhere near 1700. However, that could be some, if this was the option, it would not have this crucial sp2 hybridized peak there because there are no double bonds between carbon atoms. So we know the answer is the cyclohexene. I hope this was helpful. IR spec can be pretty tricky, but it's extremely important moving forward with organic chemistry and any other analytical sort of chemistry. If you found this insightful, make sure to like, comment, and subscribe for more. Thank you very much. We'll see you in the next one.